Hello. I'm just gonna set up the stream here. Get all my docs sorted here. Let's see, let's change this to live chat as well as this one. All right, we Gucci. I think at least. All right, welcome to the stream. If you're watching this in the future, um, yeah, last episode we started creating some different structures relating to shadow mapping. Yeah, I've been playing a bit around with some stuff, although I haven't made major changes. I implemented some math to help us calculate the appropriate matrices. Also, I did some fiddling around with different stuff and updated the shadow pass here to include dynamic draw calls. And also I realized that the shadow map should be probably a square, not a rectangle. So let's change that. Also, yeah, I implemented the correct method for calculating a view matrix for the lights, just from the position, direction, and then a pre-specified upwards going vector. All right. So that got updated as well as the draw call. And yeah, let's use that new buffer size eventually. Let's just do a aspect ratio of 1. Yeah. Um, and let's see what we end up with in terms of our render doc output. Let's see our shadow depth buffer here. Well, as you can see, the depth buffer here gets rendered from the perspective of the lights in our scene. As you can see here, the light is shining down and getting the depth information about the objects in the scene. Yeah, I'm not totally satisfied with this rendering itself. It's also because the viewport is limited, I think. So let's see, let's specify some values here instead. Shadow map. We could do all this is rendering related. All right, let's move this down to draw call specifics. These are system components, even though these are also draw call specifics. These are more related to resource allocation. Nonetheless, these could be draw call specifics. Here we go. So let's create a variable here unsigned int shadow map size equals to this, and let's do shadow map view BP shadow map rect as rect. Okay, and let's set our shadow map here, shadow map size. Let's create a rect and viewport. Let's see, shadow map. Viewport and rect. Let's see, let's not do that. Shadow map viewport. And let's do shadow map size here as a float. And the same thing here. And then shadow map rect. There we go. And then we bind that whenever we do our shadow pass. Okay, let's see, bind descriptor heap. Let's see, shadow pass, then shadow pass viewport, shadow pass rect here. Let's compile that. And let's see, our shadow mapped texture now should be render doc here. Let's see, let's view our content. And as you can see, we now get the correct scaling of the shadow map. From the perspective of the light. We of course need to define the angle of the spotlight in our field of view calculation. But nonetheless, our shadow map here corresponds to something looking down here. Or rather, our light's looking down on the shadow map itself. Okay, great stuff. Also, during the last episode, I also changed the pass buffer itself. And now I'm realizing that we might not need to upload separate information here, since we want that projection matrix here inside our normal pass data. I mean, yeah. Yeah, we could remove this part and just stick with the pass data buffer for each frame, since it can contain it needs to contain the light view projection. Yeah, let's just save that for the future. Anyway, inside our generalized vertex shader here, inside our pass data, we already defined our light view projection matrix array here. We'd like to output some more information here. So we want a projected, what do you call it? Projected projected coordinate space, or rather a set of projection coordinates. We will translate into normalized device coordinates, position, light space, which will be our position, position 0, maybe 0 here and 1. And we will add that to our pixel shader here. Vertex shader output. Let's see, let's just copy it directly. There we go. Okay, so we start to pass that data along. We do not initialize it yet. We have our pass data here, which actually contains our light view projection matrix. So after we have calculated the world position, normally we translate into clip space by using that world position. We would like to do the same thing in terms of translating into the position in light space. Pause W and the pass data dot light view projection here. Yeah, so we simply translate that. And that means that our shader now will have each object and their depth values inside the light space. Let's see, we also need a sampler for sampling the shadow map texture. It's fairly straightforward. We will just create a static sampler for that. I just need to look up the parameters for that sampler. Just a sec. We will do PCF kerneling and sample the texture with a border. And I think we compare, yeah. Okay, so inside our root signature here, we declare some static samplers. Let's see, static samplers. Let's add one more. Uh, let's see. Let's create the sampler. Well, the ordering here, I would actually like for the first one to be our shadow map system sampler. Let's see. Maybe it's all right that we just add it to the end, because I would have to rewrite all the sampling sampler bindings. Let's see. Shadow mapping sampler here. Let's just do this. We will do border. We will do linear, not MIP based, but filter, comparison, minimum, linear, point-based filtering. Let's see. Our comparison function here will be less equal. Let's update this. We could also just use shader register 1 and register space 1. System samplers in register space 1. Yeah. Let's see. Let's see, border color should also be set. Border color. Let's see, our border color here. Let's set this to 16, by the way. Border color, opaque, black. Let's see. The rest of the values seem correct. I'm pretty sure it's not needed to be shader visibility all, but we could do it anyway. Yeah, I'm not sure if there are any optimizations in changing the shader visibility for samplers. Anyway, let's see if everything runs and compiles. It does. Okay, so we have a sampler state here. Oh, it's a comparison state, I think. Actually, I'm pretty sure we need to do that. Let's see. Yeah. Sampler comparison state. Sampler shadow map. And we will set it to register S0 space 1. There we go. Okay. Maybe it needs to be inside the shared library here. Since we will do we include this inside, yeah, share, also delete. Maybe we want a shared library outside of this shared here. Maybe we want a separate function here outside. Let's see. Shadow mapping. And let's not in. Hello, buddy. Testing the latency on the Restream application, it seems. So let's see, we will do a header. For that, we will include it. Shadow mapping dot HLSI SLI. Oh, let's see. Redefinition. Yeah, okay. Did I? Did I not? Let's just debug compile here. Maybe it's using the wrong executable. Well, it shouldn't. No. Line. Well. Oh yeah, okay. I already defined it here in this shared library. That's why. Okay. So we will create a function here. How are you doing, FTC? Let's see. We will calculate and we will take a float 4. Let's see. Light space. Position. I'm doing all right. I'm doing all right. A bit more energized than yesterday, but still not feeling totally up to par, or rather on par. What are you working on? We would like to create a new we would like to create a new X since we're translating from let's see, normalized device coordinates into texture space UVX UV from X, rather U from X, V from Y. There we go. Oh, exciting, exciting. Good old Quaternions. Let's see. Let me see if my math here is correct. I think it should be. Yeah, I'm pretty sure it is. All right. Let's see. Texture, space, coordinates equals a float 4 with our u from x, v from y, and then our light space position cw. And yeah, I don't know if it's more efficient to write the division itself directly. Yeah, I think so. Okay, so let's see. We do like this. Well, since it's SIMD based, all of this implementation here on the GPU, it might be faster to just. This is basically the same. Maybe it has some optimization where it can copy the high word of the register, but yeah, exactly. UVs are normalized texture coordinates. All right. Let's see our pixel shader here. Shadow map should be in here. Okay, so we take our texture space coordinates and divide them all by the W position, or rather the W component, since we want a perspective divide, as it's called. We have our depth in terms of the light space, which is basically our light space position here, C value, untransformed, or rather no, we should actually use the transform divided one. Yeah, but they're basically the same. There's no real difference between GLSL and HLSL because they all compile down to the same instructions on a GPU. So the underlying hardware doesn't change between the languages, and therefore they will be almost 100% identical, at least when they compile down into assembly or instructions, machine code. Yeah. Okay. We could store this. We could also just grab it. Well, anyway, we want to grab our shadow map information here. Let's see. It doesn't have a method called that. Let's see, texture 2D, HSL, whatever it's called. What do you have in mind specifically? It should have. Is it deprecated? Shader model 5. Objects, texture 2D. It should have the. Well, why does it? Oh, maybe I haven't defined the type correctly. There we go. Capital T, boys. Capital T. Mid level 0. We will store our. Yeah, let's just get the width and height. And width, height. Not that they matter too much. Let's see. Let's see. Okay. So we grab the dimensions. Since our texture is rectangular, we know that the x and y coordinates are the same scale. So we can calculate a delta coordinate, which is 1 divided by We can just use the width, but of course we need to cast it as a float here. Then we want to create a kernel, float to kernel, where we set our negative delta coordinate as the upper left corner. Then we set the midpoint here, which is of course the 0, and then the negative value here, and then the last part of the first row of the kernel, which is delta coordinates minus delta coordinates here. Whoops. And so this is the middle row of the kernel, and then the last one here. Let's see, float. This will of course be delta coordinate on the y and the same on the x. Yeah, so this is our kernel. HLSL is just a programming language, so it has nothing to do with the underlying shader structures. GLSL doesn't have compute shaders either, but OpenGL or Vulkan has compute shader access. So if that makes sense. So DirectX12 does have compute shaders, so therefore you write compute shaders in HLSL. Yeah, exactly. It's basically a way of linking to the pipeline, or rather the graphics card itself. The compute shader is just a specific version where there's only input and output. There's no other attributes to that pipeline. That's how you do AI on the GPU. You simply use the compute shaders and write your AI algorithm in HLSL if it's Microsoft, or GLSL if it's Vulkan based, or Open CL, or what it's called. Can't remember. All right, so we have our kernel here. We will apply our kernel. We will unroll since it's faster. And we have, whoops, face forward. What? I didn't see what happened. Okay, let's see, for I++ here. shadow factor equals 0, or cumulative, or rather light accumulation here. All right, thanks for dropping by, and thank you very much. I hope to see you later. Have a good one. Okay, so we will use our kernel here to sample our shadow map. So we will add to our light accumulation here by sampling our G shadow map sample compare for the first MIP, and we have our sampler shadow map here at the texture space coordinates XY plus whatever kernel offset we have, kernel I, and the compare value is in itself the depth here. We could just do this actually instead of storing that, and we want simply the result here. The return value. C component. Yeah, I don't know why it returns a float 4. Well, excuse me. Anyway, that's basically our shadow factor sampling. Let's see if everything compiles. It does. Okay. So inside our pixel shader here, we should be able to call the calc shadow factor. Let's see. Let's set our shadow factor here to an array of 3 floats. And set whatever we want to use for that compute lights. We will have one spotlight, I think. Let me see, shared lights, spotlights 1, so we will be calling the spotlight part of the algorithm here, spotlight. Hello, Fanmia. How are you doing? How are you doing? Let's do shadow factor here. Decompiler, what is that? Let's see, let's define this. Shadow factor. Okay, so the last component here is for the okay. That sounds interesting. It's basically some kind of reverse engineering, right? Position light space. Yeah, okay. That makes sense. Okay, let's see what happens. Okay, we have a problem here. Okay, I forgot to delete the macro here. Well, nothing is really happening, is it? I can't imagine. I can't imagine. All right, so our shadow factor here doesn't really get calculated correctly. Oh, it's I forgot to add it here. That is why. Okay. Oh. Yeah. All right. Num-static samplers. We need to add that one. Hello. What's up? Maybe I'm not allowed to actually created in a different shader register. Let's see. Actually, we need to add 5. There we go. All right. We do have some sampling, at least, but it's not entirely working correctly. Yeah. Okay. Position light space. So I mean, what happens if I move this? Nothing really. Let's see. If I change this to X, everything will look as it did. Yeah. Let's see. Maybe my calculation here for a spotlight is off. Maybe I have an error inside this. Let me see. What if I don't do the perspective divide here? Oh, did I change that back? What was this C value here? Well, without the perspective divide, I won't get anything. Also inside a root signature here, maybe. Let's set the sampler value like that. Let's change the ambient lighting. Um, yeah, so maybe I'm not doing it correctly in terms of the compute spotlight algorithm here. Mm-hmm. All right. Well, something goes wrong in terms of calculating the shadow factor itself. Let's see. Let's debug this inside render doc. because I want to make sure that my shadow map is actually correctly handled. Of course, I need to update some stuff here. Shaders. There we go. Yeah, we should have some information here at least. Yeah. Resource inspector. We know. Huh. Okay, let's see. Let's try to assess what's going on here. I mean, the lights for some reason doesn't sample the shadow map correctly, I think. Yeah. Oops. Uh, should I? Do you think I'm too loud or? Yeah, that doesn't change anything. Oh, there's an error right here. Okay. Let's get this back to width and height without any levels. Okay. That looks a bit better at least. I mean, okay, let's try reducing the ambience here. Oh, so we can actually see the shadows here. So I'm thinking that it's mostly related to the cone calculation itself, because it seems like it's way off here. It's not centered. It's not centered at all. But it does cast shadows now. Okay. Let's do a very small light, amount of ambient light here. so we easily can see our shadow. Yeah, we definitely need some adjustments for the shadow mapping itself. Let's try adding a static object where we raise it a bit. Yeah. Some of these things are off, but at least we have our shadow map being created here. Just a sec. So we have some degree of shadow casting here. Let's see. It should also be dynamic somewhat, meaning that if I move Paul here, the part of his shadow here should also move, which it does. So yeah, the center of the projection here is obviously off. So we need to work on the frustum itself. I think at least. Let's try doing this frustum here. Well, we're still far off center. And if we get our light, we build our cameras here. Oh, lights are created in the level, of course. Calculate lights. So the position is, well, I think it might relate to the calculation of the x and y coordinates, because up here, because I don't think we have the correct offset inside the shadow map texture, because whenever I debug the shadow map here, let's see, you can see that the shadow map is actually center in terms of the objects here. This is from the viewpoint of the lights, where we do our shadow computations. Just a sec. Okay, so it does seem like it's centered. So it's the translation between the light space positioning here. Let's try and just remove this and see what happens. Then we're off center to the different side. We also do too little sampling. So yeah, it's definitely related to that part of the algorithm. At least I suspect. Let's see. So we're translating the X here. Well, the lights should be directly above it, so I'm not sure that this actually makes any sense. Yeah, so we should actually see a lights that were completely on top of this. I mean, it's at the center of the scene. It's right here, but it's offset on the x-axis. So what about our scaling here? So if we divide, multiply by 0.5 here, we get something that is more like the correct scale. Then we want to offset. Let's do +1. Which will be clamped, of course. -1, or rather half here. Oh well, the wrapping method here, did I set that correctly? Mode border. Let me see, because linear point. Also, if I change into this, I'll see something that is yeah, that makes more sense, doesn't it? Because the spotlight should shine correctly, but we're still not mapping correctly here. Okay, so inside our shadow mapping algorithm here, let's see, let's double this. It still doesn't change anything. Okay. We're not sampling correctly. Plus 0.5. 75. We can't really Let's try creating a projection space matrix here. Temp mat. Do I have any? Let's see, float HSL. Row 1. Okay. Let's see. Let's set the matrix here. Minus 0.5 here. And let's do a commented text section here. Where we simply set load for texture space coordinates equal to multiplication of our light space position here and our temp mat. And then we will set it like this. Let's see if we succeed in transforming into, yeah, there we go. So it's related to the actual way I do translation. Okay, instead of doing this on a per shader basis, we will do it outside the shader. Yeah, so the coordinates needs to be transformed before they are multiplied by the position vector in of itself. Okay. There are still some problems with the edge itself on the bounds of the shadow map. It is fairly square, but it does work nonetheless. Yeah, so we would probably want a over-inclusive angle in terms of the actual shadow map here. Right now we're just trying to calculate it manually. I think the shadows would get blurred on the edges of the lights itself. Let me see. So if we increase the angle of the light view projection to something like this, And then maybe 15 here. Simple loading. That does look a bit more reasonable, doesn't it? So yeah, we cast a shadow that gets proportionately bigger towards the edges of the light volume. And yeah, it ends at the edges. You can see a bit of light bleeding here on the soles of our character. Okay, let's try spawning some objects. Let's see. Let me free the mouse here. Add a static object. The objects cast shadows on each other. Let's see if I move it to the left here. It will be completely in shadow if I do only one. That seems reasonable. It's not perfect, but it seems reasonable. Yeah, there's definitely some playing around with this algorithm in terms of how to calculate the view projection matrix and maybe do even some kind of feathering around the edges of the shadow map, or what do you call it? Feathering, kind of blurring or softer edges. But yeah, I think that works pretty neatly. So basically, we could move the light itself. We should definitely implement some more manual computations here, or rather automated computations on yeah, there's also that bug I haven't fixed yet. Well, now the shadow even gets cast right there. Maybe it's related to the box normals, actually. It might not be related to anything else here. Yeah, because the tip now does get translated correctly. I'm not sure that is that realistic. Maybe it is. That shadow does get cast correctly. 45 degree. Okay, it does change a bit, right? Yeah, it does skew. So, yeah, that does seem correct. Okay. Yeah, that's decent. That's decent. That's decent. we have shadow mapping. And it even works with dynamic objects. Yeah, that's great. Yeah, I want to fix the way that the frustum gets calculated for the light itself. Let's see, calculate frustum spotlight shadow mapping. We don't want directional. Perspective. Okay, I guess I... Okay. Yeah. Okay. Let's see, does he write anything about the... Yeah, so the near and far plane. Uh, yeah, we don't need bias computation since they're done automatically by the shader. We have fairly good aliasing, anti-aliasing. Let's see. Yeah, we could bake the shadow map itself for the static objects. Yeah, and you can do culling in terms of the shadow map generation itself. Yeah, we would like to do some cubicle shadow maps as well. It would be fun. Basically to have a game that is lit by point lights and spotlights. At least for fun, we could always implement, or rather we already have an implementation here that allows us to use directional lights. We just need an orthographic matrix instead on the actual light view light projection. So we basically support directional lights right out of the box with this implementation here. Let's do a shadow factor here, X. And well, the way that we get our point lights here would be somewhat different. Although, yeah, that would mean that the pixel shader itself passes along the point light information if needed. All right. Yeah, so let me just do a overall to-do file inside of this directory here. Add new item. Data. Don't tell me that I'm not allowed to create a text file. Anyway, we will do a bug fixes global to do bug fixes global, and that's CPP. Rename that txt. Need to do bug fixes in general. UI fix that period separated numbers do not render correctly. Let's see. Inside the renderer, I wrote something. We did that one. Renderer. Okay. In terms of object computations, in terms of calling threaded, draw call, recompute before rendering. Yeah, I think each object, static as well as dynamic and transient, will be called before rendering submission. All rendering work threaded in extension of the calling yeah, we will do that. Draw calls for static objects might reuse the allocations on the static allocators and dynamic as well, if possible, or else just copy new ones. Transient objects. So yeah, we will do transient objects as submitted or copied and submitted as needed. Yeah, so we will devise a system that will do that, that is scalable. Okay. Great stuff. So let's see. It's not a bug. To do in general, calculate the proper frustum details in terms of the shadow map for spotlights. Okay. So let's see. Can we find a great graph of a spotlight here? Let me see, can I find a good model that we might use for our Spotlight, computations. Because we obviously want to improve them. Let me see, have I lost sound? No, I haven't. Yeah. Where did I have an issue then? As far as I know, I haven't changed anything, right? Oh, I shouldn't include this, of course. Yeah, so maybe the projection of the actual shadow map view matrix is not, or rather the projection is probably not right. The view matrix might be wrong. I think it depends on how we compare to the calculations of either. So we want to make sure that the kind of like frustum that we create ends up being correct in relation to the spotlight. Mm. All right. Let's see, inside our lighting implementation. Yeah. Falloff start and Falloff end is basically the far plane, right? Let's see. Falloff end. Okay. And our thing here. Okay. Yeah. Let's see if we increase the step size here. Let's see. It still projects a bit too much, doesn't it? It also appears floating, but that might relate to the physics system itself. Okay. Maybe it's just the bounding volume. That's not entirely correct. Yeah, but it does appear a bit floating here. Let's see. Whoops. Anyway. Okay. Spotlight. Implementation C++. So for instance, we want some kind of near plane projection of frustum. Yeah, so if we change now it will hit the floor, right? Well, not entirely. Yeah, but it will have fallen off. Let's see, let's start the fall off at 11 here. Yeah, and then this will be 12, and it should still be fine, right? No, but the light gets more intense. Mm. Let's see. We could do some computations in. Okay. That looked weird, right? Uh, yeah, I think I need to redo the normals for the objects since they are probably not correct. But and you can see here the edge of the shadow map is not following correctly here. Okay. So the fall off end itself is like where the actual cone itself ends. It's sort of like the whole length of the spotlight itself. I think if we increase the spotlight power here, we might also get a spotlight that is wider. It doesn't seem like it though. No, it doesn't affect the size of the cone, but probably just the intensity itself. Yeah, so the cone is calculated like that. The angle itself. Yeah. So it's basically a triangle, isn't it? Yeah, so yeah, so inside our shader here, uh, so the Falloff end is basically our light end. And the calc attenuation, let's see, saturate. That's the point light, spotlight. Uh, so let me see. Mathematically, we need something like calculate spotlight cone light direction. Yeah, since these are normalized, dot product, max dot product, let's see, max dot product, normalized vectors should be 1, right? Yeah. So this will be between 0 and 1. And we yeah. So the position minus the origin. Should be and normalized. Yeah, okay. That's just the light computation here. Let's see. So we want to compute that. Falloff. Strength. Yeah. I know the parameters here. Let's us calculate the light contribution, but I was wondering whether there was a smart way to actually compute the the yeah, okay, so this is the length. And when we saturate, we get the degree of fall off. Yeah, we can always calculate the length and the direction, which means that we have one side of the angle. Let's see, so so 15 should be like the radius, right? I mean, Um, okay. 20. This should be close to the whole scene, right? Yeah. Okay, so we can actually calculate the sides of the triangle from this. Yeah, so in order to calculate our projection stuff here, let's see. So our g vector end position is equal to math scale vector multiply scalar. Let's load our light direction here and get our Falloff end. And then we want the distance to be math subtract our inputs from subtracted with our light position. And let's do distance equals math dot distance, and then we have float dist equals distance here, just temporarily. Let's print that just to be sure that our math got correct. This total length of light vector squared. Let's see, the square root of 700 and not programmer scientific 729. Let's get the square root 27. Well, that doesn't seem correct. Am I supposed to flip these? No, it's the same. Let's see, let's print the npos. That's the register function I want to use. Print register and npos. Npos here. Yeah. Distance. Minus 27. Let's see our position. Is that uh, that's not correct at least. 27. That is not correct. Also, let's see. Print register. Light per pos. Yeah. Let's just make sure it's not negative. Well, no. Well, I actually think that this needs to be negated. Uh, because we subtract the origin from it. There we go. Well, that's not correct either. Okay. Light pass, end pass. Well, now I know. I'm not supposed to subtract this. I'm gonna add it because we're gonna extend the yeah, along. Yeah, that was silly. Okay. So let's get our end pass here. Start pass. So our start position or end position. So basically, our end position. Yeah. And let's do vector subtract here. Although it's not correct right now. So maybe just vector add. So our distance vector here is actually our real end position. Let's see. Let's add these together here. Then we have our distance, which is our vector subtract from our start position here, our end position, and then we square it. Let's see. There we go. Yeah, distance 15, which is correct. Well, we have our distance actually already in our Falloff distance. Yeah. But we can get our end position. Hello. Not much. How about you, buddy? Yeah, that sounds exciting. Whether you should start learning game development, or I'm not sure what you're asking. Yeah, so if we it depends on how interested you are in programming. If you're really interested and want to learn how to do game engines from scratch, I suggest learning something like C. If you're not really that interested in the actual programming but want to do more game development stuff, you could probably learn something like C# and use Unity. But if you want to do game engine programming, I think C or C++, even though C++ is a bit harder to get started with. Okay, if we only start the Falloff at 12, I think the cone will... No, it will just get stronger. It will end out here anyway. Yeah, exactly. Okay, so the Falloff is like... It's basically... That's great to hear, man. That's a great start. So I think the cone itself, you know what? Let me just add a debugging reference here. Let's see. I want to be able to draw the debugging information in terms of the light so I can visualize it. Let's see. Debug visuals here. Points. OB spheres. ABs. Yeah. How many lines of code? Let's see for... I don't know. I don't know. I really don't know. Let's see. Our renderer here is... yeah, I have so many comments. So about 1,000 lines. Our application layer here is about... also 1,000 lines, and our level system is 1,000 lines. So maybe between... I don't know, probably around 5,000 lines of code or something. There's so many comments everywhere, so old stuff I don't use. So yeah, but there are different. There are a lot of files. I don't know if I can see it somewhere. Visual Studio, lines of code without comments. Okay, I can do some computations, but I'm not gonna bother. I think it's around 5,000 lines of code, approximately. Okay, so for each of our lights, I'm very old. Do you know the expression never ask a woman her age? Well, that applies to me too. Okay. Okay, we create one light. And let's do a debug primitive here. Whoops. I've been programming. Do you want it in total amount of hours full time or part time? Because I'm only doing this as a hobby, so um, the months will be way higher in terms of how many months I've really been doing it. But yeah, well, if I had to calculate it all into like someone who did a full-time job, like 40 hours a week, I guess I would have been programming for maybe half a year, maybe something like that, if it were full time. But since I'm doing this in my spare time, the time frame is obviously way longer, so therefore it's been a couple of years on off. Yeah, full time. So that means a 6 months of 40 hours per week, if that makes sense. But that's an approximation. I really don't know. I don't have a sense of it. All right, we can simply just map this directly to the light position here. Thank you very much, man. And you too. Let's see. So let's do something like this. I don't work as a programmer, so I have zero income in terms of programming. I do another full-time job, which pays the bills. Not position 2 here. Yeah, exactly. I have zero income from this hobby. Not even the YouTube thingy does anything. Okay, so let's see. I should be. Oh, I of course need to add it. Debug AABBs and place back this temp here. Okay, now we should see the light source getting rendered. Yeah, the light source is up here now. So I'm thinking, yeah, how are you liking it? Yeah, it's really nice. Okay. Also, if I change the Falloff thingy here, let's see, 13. I'm programming a game engine from scratch. Right now I'm doing the shadow mapping here. I'm gonna calculate the so-called frustum in terms of, okay, let's see, of this lights here. Let's see, 14, does that make a huge difference? Well, it definitely shrinks the whole thing. Maybe 12.5. And I'll get a better sense of it. Let's see, so thank you very much. Thank you very much. I still think that there are some adjustments to be made in terms of the whole shadow mapping here, but we have dynamic shadows, as you can see here. When I move the object here, everything gets dynamically computed. But yeah, I would like to calculate let's see. No, no, no. Um, no. I'm not even a programmer per se, so I work with something else. I work within healthcare, so I'm nowhere near somewhere where I can work with game development. Well, I don't know. Maybe I'm 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 not gonna get employed by a big studio because yeah, I'm not living in the right spot for that, and yeah, I don't think I want to be a part of a big corporation anyway. I mean, in the future, it's not. I'm from Scandinavia. How about you? Uh, calculate spotlight cone position. Yeah. Are there any great companies there, or do you have to move for it? Yeah, yeah, I know where Uzbekistan is. Oh, that's sad to hear, man. You think you'll end up moving, or? Mm. Yeah. Do you have any specific countries in mind? Yeah, okay. Nice. I think that would be awesome. I don't know how old you are, but if I were younger, I would probably study abroad as well. But it's almost 10 years since I graduated. So, well, you have your life ahead of you. Okay. Yeah, sorry, my headset got messed up. Thank you very much, and thanks for dropping by, and good luck on your future project here. Um, Take care. Okay. So let's see, we can use our debugging utilities here to track our edge of the cone. This will not work in terms of showing the light correctly, but maybe we can we can add a point here. We'll do some, whoops. Actually, what happens when I do that? Oh, I can simply flip the tabs here. Okay. Well, that's way better. Okay. I think I prefer that. Oh. Okay. We can do some in-place spec here stuff. We can draw a point. debug primitive point, and let's see our let's do like this, because I should be able to simply see this whenever I hover over the primitive. Yeah, there we go. So that's way better. So I think we simply set the center. Let's see, point dot position 1 here equal to something raised on the y-axis here. And let's see, point color. Let's do a thing like this, and we place back this point. Whoops. This is only 3 floats. Okay, this should give us a point floating in space whenever we enable the debugging. Yeah, it's right there. Okay. Great stuff. So let's see inside this. 0 lights pointer key light. Let's add let's store the float here. Let's see, g vector point p pos. And let's calculate math vector add r math load float p light position reference and math vector scalar vec3 scalar vector scalar scale. Scalar. Okay, let's just do math add vect scale. Here we go. and we pass in the light direction here, and then the P light Falloff end. There we go. Let's try that. Okay, it ends down here. So we see our point getting calculated like that. So if we were to calculate well, let's see, if I just add one little yeah, we actually do get some light calculation since this extends beyond that. Okay. Yeah, so we are in the outer edge of the cone itself. Inside here, when we attenuate, this is basically the distance between the point and the lights subtracted from the fall-off end divided by itself. Since we're using 0 for the fall-off start. If we were to change this to something like 11, we might see more lights actually being computed. Or if we were like, yeah, we don't want to fall off. Let's see if we, yeah, as you can see, the cone of the lights here is actually fairly big. The cone is still the same, but it ends before, so it's like sort of uh, I'm not interested in finding the actual fragment calculation because we do that already. Calculating light cone distances. So we scale it with the relationship between, well, since it's oh, view, matrix calculation, spotlight, cone. Let's see. Yeah, we basically need to spotlight. We don't directional lights. No one can tell me how to calculate the correct matrix. I'll probably do a Stack Overflow question in terms of calculating that. I mean, we have the position, but how to project the spotlight projection volume? Yeah, so you specify a cutoff angle. Is it just Let's see if I change this to the same level here. Let's just do 13 because it looks prettier. Yeah, so we will have a perfectly intense spotlight here. That doesn't fall off at all. This will be division by 0. It will probably be 1. Okay. 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 Let's see. View, projection, matrix, spotlight, calculation. I already do that. Okay, maybe I should just mm, yeah, I'm pretty sure I calculate the what do you call it? Let's disable this for now. I'm pretty, oh, oops. I'm pretty sure that, yeah, we use the Falloff in here as the, but I really don't know about the angle. Let's increase it to something absurd. And see how the shadow maps turn out. Like maybe something like 3. Yeah, that's out of bounds, I think. Alright, 0.5. I mean, manually tuning this is also alright, but I prefer not to manually tune it. Anyway, yeah, I'll look into that in episodes. Because it's too boring to mess around with right here today. Um, anyway, I've been going at this for approximately 3 hours. Next we will do point lights. that involves a lot of cube mapping and so forth, but yeah. Let's do something like this again. It definitely works. At least seems like it's working. Yeah, it is working, but we could also do something like maybe add a bit of an angle to this. Do we even normalize it inside the direction computation, direction, normalize? Do we even use the... No, we don't use the directional vector at all. Huh. We might use it to do some testing. Yeah, but anyway. Our stuff works. So yeah, I would also like to do a point light implementation of the shadow mapping, which means that um, we could create a light that shines for a certain distance in all directions, and uh, we should do shadows cast in all of those directions. You use a cube map for that. We need a probably a shader to or a pipeline to create the cube map itself for that particular light. Um, yeah, the only things that are left in terms of the shadow mapping here for in regards to the spotlight is optimizing the shadow map view projection matrices. Yeah, but I'm gonna do a break. Um, yeah. Um, if you're watching this in the future, I'm sorry about the latter part. It ended up being a lot of math researching with no real outcome. But yeah, in the first part of this episode, I obviously um, let's see, maybe this article or rather discussion will help me. But yeah, I implemented the spotlight-based shadow mapping. In the next episode, I'll do the directional shadow mapping, or rather not directional, because that's basically the same implementation. You just use a directional light view and projection matrix instead. So that's basically the same implementation, but point lights need to be cube mapped. So we will check that out in the next episode. All right. Thanks for watching. If you found it helpful, entertaining, or just soothing that I am no expert, please consider liking, commenting, or subscribing, or even supporting the channel. All right. Thanks for dropping by. Hopefully I'll see you around. I might do the next episode today. Yeah, we'll see. Anyway, thanks for watching. Take care.